Hello, and in this video I'll be covering drag and terminal velocity, which is topic 3.2 if you're studying OCR part 2 of the specs, so 3.2.2. And to know about air resistance, you need to know about friction, which I kind of covered in the last video, but friction, so you have a ball, is just moving, opposes the motion. So if a ball was moving to the right, friction would be acting to the left, trying to slow it down if it were. And an object moving in a fluid, so a fluid is a gas or a liquid, it experiences fluid friction as opposed to this, which is between solid, which is contact friction. If it was something falling through, say, a container of water, that experiences fluid friction acting in the opposite direction of motion. And unlike contact friction, fluid friction increases with speed. There. And it's affected by a number of things. So it is actually affected by the density of the fluid. So water, washing up liquid, that kind of thing, all have different densities. The coefficient of drag, and the cross-sectional area of the moving object, so whatever the area, we'll say that was a little ball sphere. And lastly, it's affected by the velocity of the object. I can't write, my tripod's in the way. It's really annoying. And they all act to change fluid friction. This is worth mentioning actually that fluid friction is pretty much just air resistance or drag. Terminal velocity occurs when the weight of the object falling is equal to the drag or the air resistance that is opposing the motion. So say something was dropped from high up, say a parachutist jumped out of a plane. So there's various steps that would happen during the free fall of the parachutist. So if we model the parachutist as just a little circle like that. So at the moment when he jumps out of the plane, or she, the only force acting on it will be the weight. There'll be no air resistance because when t is 0 and it's just literally jumped out the plane, the only force that is acting on its weight. So it will have actually an acceleration on Earth unless it's jumping out on Jupiter or something with 9.81 meters per second squared. As he falls, so say t equals 5, we have same weight because weight is actually constant. It's a constant force because your weight doesn't change. However, you have also on it acting air resistance or drag. That is because as velocity increases, which it will be doing as time goes on, drag actually increases. And as I said in the beginning of the video, a factor that affects the drag is the velocity. As the velocity increases, the drag or air resistance increases also. So when does this reach terminal velocity? That arrow is not as big as the drag. The weight is not as big as the drag here, so it's still actually accelerating downwards. I don't know if these are right. I don't know how long it takes for something to reach terminal velocity. But when the weight of the skydiver is equal to the drag, or the air resistance, that is when terminal velocity, or TV, I'll just abbreviate it to, is reached. When the drag equals the weight. Here, that is when it stops accelerating, and I don't know why I'm putting exclamation marks after everything, has a constant velocity, or i.e. a resultant force of 0. If you want to know what that is, watch my last video. And is when it has reached terminal velocity. So, what will happen when the parachute opens, or the parachutist opens his parachute? Well, the air resistance acting on the parachutist will be much higher or larger than the weight acting downwards. This will therefore slow his velocity. I can't do that thing. And that is because there is a larger surface area, so there is a bigger air resistance or bigger drag that is acting on the parachutist. Therefore, this will actually cause the parachutist to slow down until the drag equals the weight again, and then terminal velocity is reached again. But this time it is much smaller than when the parachute wasn't open. So to draw a graph of the parachutist, to have velocity here, let's just call it V, and this would be time on the x-axis. Well, you'd have decreasing velocity, so let me change my pen to annotate it. This bit here is where the air resistance is increasing, this flattening curve. That's where air resistance is decreasing, or increasing even, and therefore the acceleration is decreasing. So it's going down there on this curve. This bit here is where terminal velocity is reached, because it has got a constant velocity, weight must equal the drag, and therefore there's no resultant force on it. At this point here, that is where the parachute opens. At this point here. And that means that, as said here, the velocity decreases. So here. And this is where the drag equals the weight again. So this is actually a new terminal velocity 2. And then this bit here, where it just kind of cuts off, is obviously where the parachutist lands. You need to know how to measure an terminal velocity for an object such as a ball bearing in laboratory conditions with that equipment. There's several ways of doing this, but one way, that I was taught at school, is that you have a large tube such as this, and you fill it up with a viscous liquid such as washing up liquid, something like that. You fill it up, and once it's filled up, you need to mark fixed distances on the tube with perhaps elastic bands or a marker pen or something at fixed distances. So like this. That's not necessarily fixed, but you get the idea. Once you've done that, you need to drop a little ball bearing, something like that, not too big, into the liquid, or the washing up liquid. And once you've done that, you need to start the stopwatch immediately once you've dropped it into the liquid, and time when it passes each marker. For instance, here it passes at t equals 1.1 seconds, t equals 2.3, etc. Now, a tip which I did was I actually used a video camera or my phone to record it in slow motion, so that it could be watched back in slow motion and get some more accurate value of the times that the ball bearing passed each band. I think that's quite helpful because it reduces random errors. Also, to reduce random errors, you can repeat it. You have to repeat the experiment several times. And to get the ball bearing out, once it's at the bottom, a tip would be, like my teacher told me, was to use a little magnet and then just drag it up really slowly until it's out, and then you can re-drop it in as many times to repeat the experiment to reduce random errors. Further to this, you also can reduce parallax errors by keeping your eyes level to the elastic band that it's passing, that the ball bearing is passing. That reduces parallax errors. After you've done this, you need to calculate the average time taken to pass each elastic band. So say this distance here, you wanted to calculate the average speed for. So say that distance is 10 centimetres between each one. Well, you know that the distance and the time, so you can actually work out the speed by doing the distance between the bands over the average time that you've just measured. So say for this, the speed passing the first band would be 0.1 metres over 1.1 seconds, which is something. And you do this for each band that you've got on your tube. So you'd have loads equals s equals s equals, and you'd record them in a table. And eventually you'd get all your results. And when the velocity, or the speed here, it stays the constant, so say it's 0.67, 0.68, 0.67, something like that. So you can't actually see what I'm doing. I'm only written a few fake numbers there. That's when you know that it's reached terminal velocity, and that is the object's terminal velocity in the tube, and that's how you measure it in a lab. It's pretty standard, it's pretty easy to remember, it's not that hard. Anyway, that's it for this video. Next video, I don't know what I'm doing. I don't know when I'm doing it. Probably be mass, weight, centre of mass, that kind of stuff. So for the next bit in the spec, I'm just going to do it in order. But yeah, that's it. So thank you, bye bye.